This being the third installment of section 5.1. Continuing on, we saw last time about the limit L of a sequence A sub n, or an. The limit as n goes to infinity of an is, well, it might not exist, the limit might not exist, or the limit might be infinity or negative infinity, in which case it's not very helpful. But if the limit is a real number, that's what we're talking about with the number L. And to connect this a little bit further to the functions and graphs that we've already studied, this is going to be my n-axis. We'll go n equals 1 and 2 and 3, much like we do with x usually. And this axis is going to be my, I don't really want to put units, but this is going to be my an axis. My function values or my sequence values. The first one, well, what I want to show here is how a limit value, so horizontal line y equals L, or an, just the value L, if the sequence values 1, 2, 3, 4, 5, and so on, and there are better pictures in the book with more points. If the sequence values are getting closer and closer to this L value, this is a visual depiction of what it means for a sequence an to converge to a value L, to a real number L. Another way that we can look at this is think of the a sub n, as a function of n. Just like we had f of x, a function of a real variable x, we've had a function of a discrete variable, a natural counting number, n. Well, the formula could still be used for a real value, an x value. So if this is the case, then we can do something like this. If the limit as x goes to infinity of f of x equals L, then, so I'm treating it as a f of x, a real variable function, just like we've studied before. I'm taking the limit as x goes to infinity along the real number line. It's much the same as the counting numbers going to infinity along the counting number line. If this is the case, then the limit as n goes to infinity of a sub n is also equal to L. So if the limit of the continuous variable function is L, then the limit of the sequence, and that's the connection between the two. You can have your y equals f of x or your y equals an as the dependent values. The reverse doesn't hold. Just because sequence converges to a value L, it doesn't necessarily mean that the function converges to L. The function might not even be defined for the numbers in between the whole numbers. This is not a two-way street. If this, then this, but not necessarily the reverse. All right, so we need to look at some of the properties of limits that are going to help us decompose complicated limits into simpler limits that we can then either evaluate or maybe decompose further and so on. So these are the so-called algebraic limit laws. And these are the same as the ones for the limits that you looked at in Calculus 1 at the very beginning of the semester. They're the same properties. We're going to look at them in the terminology of sequences this time, though. So if the limit as n goes to infinity of an is equal to a, capital A, and the limit as n goes to infinity of bn is equal to capital B, then we get the following properties. This first one's a little bit cryptic, but the first one says the limit as n goes to infinity of c equals c. Well, I didn't mention c before, but c is just some constant value. And the limit as n goes to infinity of c, it doesn't change, it's always c. So that's my sequence a1 equals c, a2 equals c, a3 equals c, and the limit is a constant sequence, much like a constant function. The second one is that the limit as n goes to infinity of CAN is equal to, well, they show steps here, and I'm going to do it for this one, just not the rest of them. But that's C times the limit as n goes to infinity of AN, which is CA. Remember, the limit as AN goes to infinity is A. The limit of the sequence formed by multiplying each term of the original sequence AN by the number C has a limit of C times that same limit, C times A. So it's very much like factoring out this constant C. And you do that with integrals also. You can factor out a constant factor, bring it outside of the integral, bring it outside of the limit, bring it outside of the derivative even. This one, the limit as n goes to infinity of AN plus BN. So the limit of the sequence whose terms are the sum of these original two sequences, AN and BN, AN plus BN. Well, that's equal to A plus B. And you can see a little bit more detail in the textbook, but what it is that the limit of the sum is the sum of the limits. And that's what it says right here. Now, also, we can get a little more mileage out of this by saying plus or minus. So the difference of two sequences, really, but it's the sequence whose terms are the difference of the original sequences. Here's one that applies to limits, but not derivatives and not integrals. This is a product of a limit of a product. So to start with, the limit as n goes to infinity of AN times BN, or just AN BN for short, is the product of the limits. And then finally, we can do this with a quotient also. Another thing that you can't do with like this one, you would have to use the product rule for a derivative of the product. We're not looking at a derivative, though. We're just looking at a limit. This one, similarly, it's nice with sequences. Not derivatives, not integrals, but if we have the limit of the quotient, so the terms of my sequence here are AN over BN from the original ones. It's the limit of the quotient is equal to the quotient of the limits. That's A over B in this case. Okay, so I've got some examples to demonstrate how to use these algebraic limit laws. Page 435 is where they state these laws and where these examples come from. So let's look at a few of these. And this is called example 5.3. It says for each of the sequences to determine whether or not the sequence converges. If it converges, find its limit. So for part A, they give us 5 minus 3 over n squared. And I want to look at the limit as n goes to infinity of 5 minus 3 over n squared. I can think of this as two different sequences. A sequence that's just 5, 5, 5, 5, 5, and so on. And the limit is definitely 5. They're all 5. And this sequence, a difference, you can make it a sum of a negative 3 over n squared, but I'm just going to think of it as 3 over n squared. That's a sequence where the denominator, as n increases, n squared also increases. So this denominator is growing as n grows larger. That's going to cause that whole term to go to 0. It grows, the denominator grows very large eventually. And 3 does not grow at all. So numerator stays where it is, denominator grows, it's going to go to 0. But I'm going to look at it like this. This is the limit as n goes to infinity of 5 minus the limit as n goes to infinity of 3 over n squared. I split the limit of the difference into the difference of two limits. Now, the limit of 5 is 5. That's a constant sequence. That was the first algebraic limit law that we saw. This one, we can look at it as the limit as n goes to infinity of 3 over the limit as n goes to infinity of n squared. Now you could look further at this limit as n goes to infinity of n squared, as that's n times n. The limit as n goes to infinity of n times the limit as n goes to infinity of n. I think you can probably see from this, though, that this is going to infinity. As n goes to infinity, n squared goes to infinity, actually even faster, or larger in any given sequence value. Anyway, this going to infinity, though, this is the denominator, and that denominator growing means that that whole term, well, what's the limit of 3? That's just 3. You could say that this whole expression here is 3 over infinity. That's not a number. It's just an idea that the denominator is extremely large and the numerator is finite. So this whole thing is going to 0. And this original limit that we were looking at is 5. You might have been able to see that a little earlier too. This part is shrinking away as the n grows, leaving the 5. So that's a fast way to do it. This is a careful way to do it. Part B is large, so I'm going to need space. So again, this is page 435, example 5.3, part B. In this one, we've got the sequence defined by 3n to the 4th minus 7n squared plus 5 over 6 minus 4n to the 4th. It looks at first glance like we're going to have to factor, but I don't think that's really what this problem's about. This is a technique that you may have seen in Calc 1, what we're going to use is a multiplication technique. Conversion factor is another name for it. But we're looking at the limit as n goes to infinity of 3n to the fourth minus 7n squared plus 5 over 6 minus 4n to the fourth. And what I'm going to do is not split it up like I did with the last one. There's a clever technique to get around that. Notice the highest power, or the highest degree term, is 4 in both the numerator and the denominator. They're the same. It's really the highest one overall that I look for. And I'm going to multiply by, well, I'm going to multiply the numerator by 1 over n to the fourth. You can't just multiply things and expect to get the same expression, but what I'm really doing is multiplying by 1 over n to the fourth over 1 over n to the fourth to keep it balanced. Scaling is another way to say it. And this is still the limit as n goes to infinity. Watch what happens when I distribute these. The 3n to the fourth times 1 over n to the fourth is just 3. The negative 7n squared times 1 over n to the fourth is, let's actually, instead of using negative exponents, that would be 7n to the negative 2. Let's write it as minus 7 over n squared. So n squared over n to the fourth is over n squared. And then plus 5 times 1 over n to the fourth is 5 over n to the fourth. I'm going to do the denominator, same thing, a little more quickly. 6 times 1 over n to the fourth is 6 over n to the fourth. And then minus 4 exactly, because it's 4n to the fourth times 1 over n to the fourth. Those cancel perfectly, leaving just the 4. Now what happens here is I can actually take the limit at this point. I can separate it and be very careful and separately take the limit of each term. But what's happening is, as n goes to infinity, 3 is just 3. It doesn't matter what constant that is. If it's over n squared, as n goes to infinity, this denominator is what they call blowing up. It's growing without bound. So this term goes to 0. Same thing here. N to the fourth. As n goes to infinity, n to the fourth goes to infinity. So 1 over, or in this case 5 over, n to the fourth also goes to 0. Denominator grows large, that term shrinks to 0. Same thing with the 6 over n to the fourth, that goes to 0. Now, negative 4 as n goes to infinity remains negative 4. And what's left is upstairs only 3, downstairs only negative 4. That's not a good form for the final answer, but negative 3/4 or negative 3 over 4, either one of those. So we were able to find that, it's not really looking at the constant coefficients. It was the ratio of the coefficients of the highest degree terms. Those two numbers came from, that 3 and that negative 4. The other ones, well, we applied this scaling factor, or conversion factor, and in the limit, those other terms, the smaller degree terms, all went to 0. In this next example, I have some good news. We're going to be able to use derivatives. We're actually going to use L'Hopital's rule. Because of the connection between continuous functions and sequences and their limits, not continuous functions, but functions of a real variable. The functions that have curves. These functions, the sequences, are dots. So function of a continuous variable or a function of a real variable is a curve. It could be a line, a really simple curve. For these, though, they're dots, and we're looking at what they eventually gather at. So for part C, our sequence is 2 to the n over n squared. So we're going to have to use a formula to get this where we can work with it. But what we're going to look at in place of the terms of this sequence is this. So an in this case is 2 to the n over n squared. That's what we're going to call f of n. So we're going to actually work with the function. That's f of n. The variable is n. But f of x would be the same thing, 2 to the x over x squared, with the n variable replaced by the x variable. And for that, we can look at the limit as x goes to infinity of 2 to the x over x squared. Put a big equal sign there because what I want you to see is that 2 to the x, as x goes to infinity, that goes to infinity. That gets very, very large. So does this. X squared, as x goes to infinity, square larger and larger numbers, they get larger and larger. Both of these are going to infinity, and this is what's called the infinity over infinity indeterminate form of a limit, which means that we can use L'Hopital, the H, if you prefer, but L'Hopital says that the limit that we're looking at is equal to the limit of, so the limit of this quotient, that's an indeterminate form, is equal to the limit of the derivative of these functions. Now, 2 to the x, I had to look this up. This is a 2 to the x ln2. It's an exponential function. You can fuss with it, and you can actually look back at why the derivative is this. E to the x is the one that I like, that its derivative is e to the x, because well, it's the same though. It's what you do for a derivative of an exponential is it's the same function times the natural log of the base. But if the base is e in the first place, the natural log of e is 1, so it's just derivative of e to the x is e to the x. With 2 to the x, there's a little bit of a scaling factor, a constant, natural log 2. The derivative of x squared, though, is just 2x. Bring the exponent down, power rule. Now, both of these are still infinite. This is another situation where if I look at the limit as x goes to infinity, 2 to the x goes to infinity. It doesn't matter what you multiply it by. Also, as x goes to infinity, x goes to infinity. So that goes to infinity also. We've got another infinity over infinity indeterminate form. I'm going to take the derivative again. Well, the limit of that quotient is equal to the limit of the quotient of the derivatives. So the derivative, this one, 2 to the x gives me another factor of ln2. So now I've got ln2 squared. Again, though, that's just a constant. It's really, there's a 2 to the x there. And the derivative down here is 2. Now this is different. This is different because the denominator is now a constant. And the numerator, this 2 to the x part, is going to infinity. So the denominator is constant, the numerator is going to infinity, this expression is going to infinity. It means it's divergent. The limit doesn't exist. It's not a finite real number. I think that this limit exists, but it still doesn't give us a convergent sequence, the limit as n goes to infinity of 2 to the n over n squared is equal to infinity. So the sequence is divergent. The first two that we saw, parts A and B, were convergent sequences. This one is divergent. I'm going to let you go ahead and no, I take that back. We should look at part D because it's got an important technique for the evaluation of limits. So for part D, the sequence they give us is 1 plus 4 over n to the nth. You might recognize this. This is actually a way of defining the number e, the natural exponential base or the natural log base. This is e to the fourth, but if you put a 1 here, it would be e to the first. That the limit of this expression. So we're raising it to the power n, this parentheses. But in there is 1 plus 4 over n. Now the n is, we're going to look at the limit as n goes to infinity. So what happens to this term? The denominator grows. Denominator grows very large. It means this term gets very small. And this expression in the parentheses gets close to 1. The exponent also grows. So we're getting a larger and larger power of a number that's closer and closer to 1. And the two kind of balance each other out, and this one works out pretty nicely. So if I look at it by itself, though, 1 plus 4 over n to the n goes to, in an informal way. Remember I said this expression, this fraction is going to 0, so this expression is going to 1, and this, as n goes to infinity, let me put that, also as n goes to infinity. So we're getting close to 1 to the infinity. Not a real number, that's an indeterminate form. I mean, it is going to go to a real number, but that's not a way to write it. What we're going to do, though, is whatever this limit is, y is what I'm going to call it. But we're going to look at the limit as x goes to infinity of 1 plus 4 over x to the x. So it's kind of an auxiliary variable expression. I'm using x here because I want to have a real variable and a limit of as a real variable goes to infinity of this expression. And what we're actually going to work with is the natural log of y. On a box here. I'm just taking the natural log of both sides to get this started. The reason is that there's an exponential, a variable exponent with a variable base. And I can't really deal with that very well. But with the logarithm of that, the logarithm of an expression with an exponent, I can bring the exponent down in front, the power rule for logarithms. So yeah, this next part is the, actually I'm not doing anything with the left-hand side, so I'll just leave that. But this next part is based on the continuity of the function ln. You can do this with ln functions, linear functions, and exponential functions. The natural log of the limit is the limit of the natural log. And that's what's going to let me use the power rule for logarithms to bring that x down in front. So that x comes down in front of the logarithm. And I get the limit as x goes to infinity of x times the natural log of 1 plus 4 over x. So I've turned this into, from the limit of an exponential expression, I've turned it into the limit of a product. I could do those also, but this is an indeterminate form that I can use L'Hopital's rule for. If I look at it on the surface, this is, as x goes to infinity, and then as x goes to infinity, this goes to 0, bringing me to natural log of 1, which is 0. This is an infinity times 0 situation. I can change it, though. I can change this, though, to the limit as x goes to infinity. I'm going to put my natural log 1 plus 4 over x upstairs, and this x factor, I can put it as a 1 over x in the denominator. This gives me the 0 over 0 indeterminate form for L'Hopital's rule. So I can use the limit of the ratio of the derivatives. Right, so it's the limit as x goes to infinity, derivative of the top. So this is L'Hopital's I'm using again. The derivative of the top, natural log. So 1 over 1 plus 4 over x times the derivative of what's inside. Now that's 1 plus 4x to the negative 1. What's the derivative of that? 4 negative x to the negative 2. I use the power rule on that piece. Or negative 4x to the negative 2. Also, downstairs, so that's the numerator's derivative. The denominator, that's x to the negative 1 right here. Its derivative is negative x to the negative 2, negative x to the negative 2, which cancels this and this. I'm going to have to do a little algebra to clean this up, but this whole thing is ln y, recall. We're going to come back and use that y to get the limit of our original sequence. Let me do this last step here. So this is the limit as x goes to infinity. All this canceled except for the 4 and the 1 plus 4 over x. I can multiply upstairs and downstairs by x to clean this up a little bit. That's the limit as x goes to infinity of 4x over x plus 4. That is actually not what I want to do with this. Sorry, I was still simplifying. What we need to do is take the limit right here. This goes to 0. I've got an x in the denominator, and the numerator is constant, so the whole expression goes to 0, and what's left is 4 over 1, or 4. And that was, remember, that was the ln of y. Y itself, which was what I called the limit as x goes to infinity of 1 plus 4 over x to the x. The original expression, well, if ln of y is 4, take e to both sides. E to the ln y is y, and e to the 4 is e to the 4th. That's just a real number. So the y itself is e to the 4th. That's the same as the limit as n goes to infinity of 1 plus 4 over n to the n. I changed the variable to x to think of it as a L'Hopital problem, but it comes out to this, just this number, e to the 4th. I want to mention the squeeze theorem that we're going to use occasionally. And it's a good way to see how you can get a handle on sequences that aren't very regular by putting them between two simpler sequences. So the squeeze theorem. There are lots of squeeze theorems, but this is the one for sequences. Suppose AN is less than BN is less than CN. And I'm just going to suppose this. It doesn't really have to be true for all n, just for all n sufficiently large. But we're really only worried about large n anyway if we're looking at limits. So if the limit is n goes to infinity of an is equal to L, is also equal to the limit as n goes to infinity of Cn. You can think of these as large, middle, and small, but most importantly, middle. Between these two, who have a known common limit. So if both of these upper and lower sequences are going in toward the same value, and the b values are always between them, then the limit as n goes to infinity of bn is also that common value of L. So the squeeze theorem. I want to do one example of that. Yeah, so this is a example 5.5, and they give this is just part A. They give us the sequence cosine of n divided by n squared. Now, cosine of x is a nice function. It has a very regular, continuous behavior. Its derivative is simple too. It's got a negative sign for its derivative, but we're only looking at not multiples of pi over 2 or pi over 4 or something. We're looking at integer values of the angle. Cosine of 1, cosine of 2, cosine of 3. And I don't know at all what I mean, cosine 1, I could probably figure out at least whether it's positive or negative, but they're not values that you learned. They're not the nice values like 1/2 or root 3 over 2 or root 2 over 2. They are kind of unpredictable, but I do know this. Cosine of n, no matter what n is between -1 and 1. That's as high as the function goes. That's as low as the function goes. So what I'm going to do is basically divide all 3 portions of this inequality by n squared to get -1 over n squared is less than or equal to cosine n over n squared is less than or equal to 1 over n squared. And I have cosine n over n squared ready to be squeezed by these two. Now, what are they doing? So this one, let's look at this one first since it's positive. 1 over n squared, the n values are growing. This one is going to go to 0. As the denominator grows, the numerator stays the same. The denominator grows, the expression goes to 0. This, they're all negative, but the denominator grows, the numerator stays the same. This is also going to 0. And so cosine n over n squared, let me write it like this, the limit as n goes to infinity, is equal to that common value from the squeeze theorem. I've got my larger sequence, my smaller sequence, my sequence in the middle, always in between those two. In the long run, this expression, not just the cosine n, by the way, it's cosine n over n squared. That whole expression is going to that common value. So that's an example of how to use the squeeze theorem. So it looks like the last piece is about boundedness. And we talk so much about increasing or decreasing. No? So let's just look at their definition of bounded. Oh, no, bounded first, then increasing, decreasing. So AN is bounded above by M if AN is less than or equal to M for all N. In other words, all the sequences terms, every term of that sequence is less than some number, less than or equal to. Similarly, AN is bounded below by M if AN is greater than or equal to M for all N. None of the terms of the sequence go below this number M. And if AN is bounded above and bounded below, it is bounded. And that's what we're really looking at. Bounded means that they don't go off forever toward infinity. They don't go off toward negative infinity. They're bounded above and below. They wouldn't be bounded by the same m above as they are below. Otherwise, they'd be just at that one value. That'd be a constant sequence. So typically, we'll have an upper bound and a lower bound. What we're really watching for is that we avoid sequences, or at least learn to identify sequences that are kind of the obvious word here, unbounded. A sequence is unbounded if it's not bounded. That's it. So either it's got terms that are going off toward any particular bound, up or down, or both even. Trying to avoid unbounded sequences, but bounded is a very valuable thing as far as finding limits, or at least finding that limits exist. I do want to mention the other definitions here just because they come up in the next section. And that's the idea of increasing and decreasing sequences. So you've worked with increasing and decreasing functions. Increasing, decreasing sequences are very similar, except they're easier to describe because we're only working with a countable number of values instead of an infinity of numbers between any two numbers. That's what makes it so difficult to say algebraically in the context of functions of a real variable. Here, though, with functions of a discrete variable or functions of a counting variable, AN is increasing if AN is less than AN plus 1. So the next term, the n plus 1 term, is the greater of the two. Or if they're the same, we still call that increasing. Sometimes they're the same, but not less than. AN is decreasing if AN is greater than or equal to AN plus 1. So the previous term is the larger one. That's a decreasing sequence. In other words, they're not, it's hard to say they're getting smaller, because if they're negative, they're not getting smaller, they're getting more negative and bigger. But decreasing means going down to the right. And if AN is increasing or decreasing, it is called monotone. So either one. If it's increasing, it's monotone. If it's decreasing, it's monotone. It can't, well, it could be increasing and decreasing, but it would have to be the same value always. So that's a constant sequence and not very useful or interesting. Increasing is monotone, decreasing is monotone. And another way to say this is that it keeps going the same way. It either keeps going up or keeps going down. It doesn't back and forth.